Hello everyone, my name is Andrey. I am a researcher at the University of Manchester, and today I want to present you our recent work on the flexibility of active distribution networks. And specifically in this work we focus on the aggregated flexibility from multiple distributed energy resources, and we analyze what additional useful information we can provide to distribution system operators, and we propose this concept of PQ area segmentation. Here you can see the outline of my presentation. I will discuss the benefits of distributed energy resources, DERs, and aggregated flexibility. I will introduce the concepts of PQ flexibility areas, and then we will discuss the main contribution of this work. It's the combinatorial OPF model for PQ area segmentation, and we will see how it can be applied within distribution networks. All right, let me start with this illustrative example. You may see here a very simple distribution network, and we can say that this is a traditional passive distribution network because it doesn't have any flexible resources. It has only 3 substations and 3 static loads. And if we want to display the flexibility of this network, for example, the total power consumption in P and Q coordinates, active and reactive power, we will see that the area of feasible operating points is just 1 point, shown here by this cross marker. So we cannot deviate much from this initial operating point. We don't have flexible resources, and that's why we say that these networks are not flexible. But now what we have an increasing amount of distributed flexible resources integrated in the networks. For example, battery energy storage systems, electric vehicles, some other resources, and we can say that these resources are flexible units or flexibility providers if they can adjust, if they have this technical ability to adjust the power exchange with the grid. And now we have this flexible network, and we can use this flexibility within the network, or we can aggregate it from multiple resources to use for flexibility services, or even to provide flexibility services between distribution system operator and transmission system operator. And the question is how to characterize this aggregated flexibility. How can we arrange these TSO, DSO flexibility markets? One very popular concept is called PQ flexibility areas, or in some papers it is called nodal operating envelopes. And you can see one example of such envelopes here, shown by this blue area. The point is that now we can change our flexibility, we can change total consumption of the network. So these flexible resources can either increase their flexible power output or consume more flexible power. The question is how to compute these aggregated PQ flexibility areas. There are many concepts proposed in the literature, but one very straightforward and simple concept that I want to show you is called epsilon constraint method. I prepared this fancy visualization for you. The point is that we want to divide the feasibility area into intervals. And in this case, we start with Q minimum and Q maximum, minimum and maximum reactive power consumption. We find 2 points, we solve an optimal power flow model, and then we set some accuracy, some granularity, and we start computing P minimum and P maximum for each interval. And we repeat this procedure, and you can see in this example that with just 120 optimal power flow problems, we have a pretty accurate representation of the boundary of the flexibility area. And this has been already done in many papers, but my point is that usually only the boundary of the aggregated flexibility is analyzed, which shows how much flexibility we have available, what are the limits of the flexibility. And in my research, I argue that this is not enough, and we need to analyze how this flexibility can be operated and how it is formed. We don't have time to discuss all the equations. This is the combinatorial optimal power flow proposed in the manuscript. The important thing is that we introduce some binary variables corresponding to the flexible units activation. And these binary variables are also included in the flexible power P and Q power balance constraints. So with this modified disk flow optimal power flow, we can track what units are activated to produce certain flexibility requests. Why do we need it? Because we can analyze certain sub-areas, certain segments of the PQ flexibility area by limiting the number of units activated. This is a very simple constraint. The summation of binary activation variables should be less than some parameter corresponding to a certain segment that we want to analyze. Let me mention that this problem is a mixed integer quadratically constrained problem. We implemented it in Julia Jump and solved by Gurobi version 10.0. Now let's go to the case study. We analyzed a realistic distribution network from the UK. If you're interested in data, we published it in a repository. This system is visualized as a graph. The size of the nodes correspond to the loads. So we can see these big nodes and we can understand where the load is actually located. One more important thing is the color scheme. Green colors show that voltage is okay, and orange and red colors show that voltage goes down to 0.96 pu, which means that we could potentially have some voltage issues, some voltage limitations, and we will see this in the results. So in this realistic network, we placed 10 flexible units with similar PQ capacities, and we started producing this segmentation and analyzing what is going on with the flexibility in this network. So what you see on this slide is the PQ area segmentation by the number of flexible units activated. This is actually a very simple picture. In the center, you see the white segment, which means that one of the units is needed to guarantee to produce this flexibility. But once we move further from the initial operating point, we need more and more units to be working together to guarantee this flexibility. And once we reach the boundary, the dark gray area, all 10 flexible units need to work together to jointly produce flexibility. You may ask, why do we need these segments? This is quite a simple idea to produce additional boundaries within the total boundary. But my point is that there are many applications of this concept. For example, this idea can be directly translated into reliability analysis. So here, for the same network, we produced reliability-based PQ's area segmentation. And in this white-red color scheme, you may see more reliable areas and less reliable areas. Let me mention that we didn't have any complex stochastic or robust models. We simply assigned some reliability coefficients to each of the 10 flexible units. And the units are quite reliable. You may see they have coefficients between 0.945 and 0.99. So each single unit is very reliable. But when we have a combination of units working together, these reliability coefficients, they multiply, we have a product, and reliability goes down very quickly. So why do we need this segmentation? Distribution system operator can, for example, want to produce services with some guaranteed level of reliability, let's say 0.9, 90%. And then we need to identify this sub-area of this feasibility area where we know that reliability is higher than the value. And in this picture, we see this dashed outline showing the union of segments that have reliabilities more than 0.9. And the first thing that we see that this more reliable area shrinked a lot, so it is significantly smaller than the overall flexibility potential of the network. One more interesting thing, I zoom this part of the figure for you. You may notice that the area actually became non-convex. So we see that once we introduce some additional parameters to this PQ flexibility area estimation, the problem complexifies a lot. And it can be very tricky for the distribution system operator to work in some feasibility areas which are not convex. So these things should be explored in the future research. Okay, coming to the conclusions, we demonstrated that a thorough analysis of aggregated flexibility in distribution networks is needed, explicitly considering contributions and reliability of each flexibility provider. In this work, we applied a simple method enumerating each PQ flexibility segment, but this approach is not computationally feasible for large systems, so more advanced methods are required. And as I said, introducing some additional metrics to PQ flexibility makes the problem much more complex. As I demonstrated in this reliability-based segmentation, we can get nonlinearity, non-convexity, and it can be hard for distribution system operators to operate systems like that. Thank you for your attention.
Are there any questions? Thank you for your presentation, Pedro from TU Delft. What's the issue with the non-convexity from the PQ map? That was not clear to me. I mean, the PQ map is just a tool for the DSO to know how much flexibility is available, right?
Yeah.
So what's the issue with the non-convexity
Okay,
here?
thank you. This is not the best example of non-convexity. We accidentally found it here. But you can see that it's a little bit non-convex, like here, here. But imagine a case where we get more non-convexity. We get like huge curve here. And what if distribution system operator works here, and then the next regime, next tower is somewhere here? So you have to cross this area because of non-convexity, which is less reliable. So you plan to operate in some reliable non-convex area, but you may accidentally leave it, you know? This is the problem with non-convexity. It's not straightforward to operate within this area. And yeah, we want to explore this more in our future research.
Thank you. Yeah, thanks for the very interesting presentation. So Matthew Deakin from Newcastle University. So I was interested in where the assumption of 0.945 to 0.99 reliability came from. This feels quite low if you have a 1 in 20 chance that one of the units would work. I guess for a dispatchable generator, it feels. What is the sort of model of the flexible unit, I suppose? Because you did mention, is this a battery? Is this what is that?
Yeah, thank you. This is a very simplified representation. I just wanted to illustrate what happens with reliabilities, and I developed these coefficients. So, yeah, they should be verified. I guess you need to introduce a system where maybe flexibility providers bid their value and also indicate somehow their reliability or probability of providing this flexibility tomorrow, you know. But these particular values, just for example, like, they don't make sense.
We have time for one more question. Yeah.
Dionysal Brandis from Purdue. When you think of an inverter, it has, for example, a current limitation. So if the voltage changes where the inverter is, you don't really have a constant P&Q, limit. The P&Q that you can get depends on the voltage. So are you accounting for that?
No. Again, we have some assumptions that P and Q capability of each unit is like a box, you know, plus minus P, plus minus Q.
Depends on the voltage.
It's not included. Yeah, could be interesting to see. I guess we will have more complex results with these. Yeah, thank you.
All right. Thank you very much. Thanks, Andrey.